Hey folks, welcome back to another video. In this video, we'll be creating this card flipping animation as you can see right on your screen using React, GSAP and React Fiber. So let's get right into it. So go to the description and check. I have given a starter file. Just clone that repo and after running npm I and npm run dev, you will see a rotating cube at the center of the screen, and that is the starter file. Also, don't forget to download other assets like images of front face and back face of the card. These are not essential. You can eventually use any image you want. So create a new file, name it public. Inside that folder, just drag those images. Inside src, you can see a components file. So this is the component that is this rotating box component is rendered on the screen, that is like rotating this simple cube. So delete this, and inside experience just remove those imports, otherwise you'll end up with some bugs. And now create another file inside components, name it card.jsx rafce. So inside it, create a mesh, and inside that create plane geometry mesh basic material. We will import the texture using use texture from react 3 ray. Inside it, just pass the sr source of the image, so slash card back.webp, map it over the material texture. We have to import the card. This looks a bit stretched. We have to give it a scale, so const scale, use aspect. First parameter will be the width, texture dot image dot width, and height is texture image height. After that, what is the ratio you want, like how much of screen should it take. So for now let's pass one, and inside the mesh let's pass scale, so it will scale as accordingly. You can see it's not stretched, but it takes the full width of the screen. So for now just pass 0.5, and you can see the card is small. Pass it 0.3, I think 0.4. This looks good to me. 0.4. To rotate this plane like this demo, we have to use our custom shader material. We can't rely on this built-in material, basic material. We have to write our custom material. So create a custom material using shader material, and it needs two things: one vertex shader and another fragment shader. So let's create another folder inside src, name it shaders, create one file, name it vertex glsl, and another file fragment glsl. Now we have to import vertex shader from dot slash shader slash fragment glsl. Don't forget to pass this question mark and raw. It will convert those, like if we write void main, it can't understand it. JavaScript can't understand what you have written there. So we have to convert it to plain text. If you remove this question mark and raw, then you will get another error. Does not provide an export name default. So we have to use question mark and raw to convert it to simple plain text. Now if I console this vertex shader, you can see this is not vertex, this is fragment. So convert it to vertex. If I refresh here, you can see this void main, this is just plain text. So that will work. So import fragment shader as well, like question mark and raw, and that's all. Now pass the vertex shader to vertex shader, vertex shader, and fragment shader to fragment shader dot glsl. So fragment dot glsl, and that's all. We're good to go. Now it will still give us some error because we have to write something inside it. So this is the boilerplate of vertex shader. If you don't understand this, then just go and watch previous tutorials. You can get those links here, top right corner. Inside fragment, you have to write something like this, gl frag color, and this is the output color we'll get. If I refresh, we'll get a green colored plane. So now we have to pass the texture. Instead of mapping it here, we have to pass uniforms. So uniforms, and uniform is a object. So u texture, and then pass the value of it, value, and this is just texture. Inside the fragment shader, we have to import it, a uniform, sampler 2D view texture. If you are not getting this color syntax, then just install this extension called WebGL GLSL editor. After that, you will get this color syntax and highlighting. Vector 4 color texture 2D view texture and UV. UV, we have to take it from the vertex. How can you do that? By creating one varying. So varying vector to VUV and pass the varying VUV equals UV. Now we have to accept it here, varying vector to VUV. And now instead of passing it as single color, we can pass the color here, and that is the texture of the image we have sent. So you can see the card is visible to us. The next task is to rotate it. So how can we rotate it using vertex shader? We have to do it using vertex shader, as we need it to rotate using those, like, all those points. If I pass it wireframe for now, wireframe, you can see these points are visible. We have to increase it. How can we do that? Inside of plane geometry, just pass the arc, an array with one for width, one for height, and this is the division 32 comma 32. So it will divide in 32 vertices. So you can count if you want. So just remove the wireframe part for now. So what we'll do is we'll move those vertices using some sine and cosine functions, obviously. So inside vertex we have to rotate it. So how can you do that? Inside vertex, everything is like, you can see this projection matrix, view matrix, and model matrix. So we can rotate it using another matrix. We have to create one ourselves. So for that, you can use ChatGPT or, yeah, anything else, or you can search on Google. You will get this simple formula, rotation matrix. So you will get this simple rotation matrix. Okay, you'll get this simple rotation matrix, and what this does is, this takes an angle and rotates our plane in y axis. So we have to create another angle as well. So let's create angle is a float variable. So float angle, and it's in radians. So let's pass pi for now. Pi value is 3.141. So you can see, okay, we haven't applied those that rotation matrix yet. You can multiply it here, over here. So rotation matrix, and if you see now, this has rotated in pi radian, so that means 180 degree. We can divide it by 4.0. You can see it's rotated in 45 degree. If I change it, you can see this rotation has been changed. So this is the formula that we can use to rotate our planes. And the shocking thing is, we can use UVs as well. So do pi by, so 90 degree rotation, and if I rotate it like that, you can see the plane is rotated in exactly 90 degree. We can multiply by UV dot y. Let's see what happens. You can see it's tilted. Why it's working like that? UV dot y is 0 here, so it's rotated 0 degree here, and it's 1 here, so it's rotated 90 degree here. So we can use uv dot y, and I think we can use uv dot x as well. So it's rotated like this. You can see card is flipping, something like this. You can create weird things using this equation right here. Okay, you can, by the way, if you don't know, you can get this equation from the pinned comment. So go there and just copy this equation and use it here. For now, just remove it. Let's create another variable, name it pi. Float pi 3.141, and let's pines instead of this. So it will give us same result. But the good thing is here, this, if we add anything to our angle, pi by 4, obviously we have to pass point values, so it will rotate it like that, and the value we add is the value that helps it to rotate. Okay, so we can use uniform for that. We can pass one uniform here, and that is u rotation, and let's pass value of 0, and we can get it here, uniform float u rotation. We can add it here, u rotation, and it's 0 obviously, so we can pass it anything, like math dot pi means 180 degree by 2 means 90 degree. You can see it has rotated 90 degree. Can you see that? It's the exact 90 degree rotation. And now we can control the tiltation of it as well. For now, let's make it 0. U rotation, make it 0. And inside angle, remove this 0.0, and have you remember that we can pass it UV as well. So UV dot y, and it will rotate like this, rotate our card like this, and we can multiply it through anything. So if you multiply it with pi, you can see this rotation is 180-degree. Card looks so weird. If you pass pi by 2, and you can see it's rotated 90-degree. So we can like use another uniform for this one as well. So we can pass another uniform. Let's name it u tilt factor and value of 0. Uniform float u tilt factor, and let's pass it here, u tilt factor. So obviously it's 0 right now, so we can't see any deformation here. But if we pass math.py, so it will rotate 180-degree. You can see this card is rotated, but we have the control to rotate it. We can use this obviously, and this is like, this will work for sure. So now what we'll do is we'll animate these two variables. We have to import gsap here and register the use gsap plugin and use gsap, pass it a empty dependency. And now we need the reference of this material or this mesh. So for now let's create another reference. And there is another bug that doesn't, it will not update those uniforms. So we have to use the React way. And how is that? Instead of passing uniforms here, we have to create another variable. Let's call it uniform and create object like that, and pass uniform like that. It will work the same, but now we have the capability of altering this uniform. Let's try to animate those factors. So gsap.to uniforms u rotation, we want to animate the value. Let's make it math.py. Let's use still factor. Let's make it 0, and so you can see this is animating. So we can create one timeline here. As we have to animate multiple properties, we also need to animate this u rotation and also this still factor. So it's better to create one timeline for that. So const tl gsap.timeline and use tl.2. Let's make it one liner, some cleaning, and then tl.2 uniforms dot u rotation value math.py. You can see it's animating. So now let's add that front part as well. How can we do that? For now, just comment this gsap part. We'll animate it later. So create another card, and instead of hard coding the URL here, we can pass it through the prop. So let's pass the URL card back.webp and let's make it card front.webp. So we can get the URL here. URL, just destructure it here, right here. If we console it URL, you can see those URLs right here. Now just remove this hard coded value and pass URL here. You can see those cards, but they are overlapping each other. We want one card to work like front and another card to work like the back side of it. We can also pass the rotation y, and for the first one, let's make it 0. We don't want it to rotate. Let's put front at the top, and we don't want the front to rotate. We just want the back side to rotate. Math.py 180-degree. So but there is one issue. This card don't have this property rotation y. So how can we rotate using that property? Here pass comma and dot props. What it will do is, it will, if I log the props, you can see it's an object with that value. So we can pass that prop here. We can destructure it right here. So dot props. So you can see it's front and it's the back side. These are it's working like a regular card that we see in our real life. Now we have to animate that. How can we do that? We have to animate. For now, don't animate the u tilt factor, just animate the u rotation value. So you can see it's flipping like that, and it's the exact thing we need. Let's pass some defaults duration 2 seconds, so it will animate slowly. So you can see the card is flipping. Also let's tilt the factor as well. So mat.py Oh my god, holy shit. You can see this card is flipping like that. And it's so beautiful. It's looking so good. But we want those two things animate at the same time. What we can do is we can pass one position parameter 0 here. So it will start at the starting of the TL. Okay. So these two things are animating at the exact same time. Now we again have to normalize this U tilt factor, as we don't want the final output to look like this bend. We don't want our final thing to look like this. So what we can do is create tl.to uniforms dot u tilt factor. Let's animate the value again, and this time make it 0. Okay, if you see, it normalizes again. So this U rotation rotates the whole plane. If I comment those top and bottom part, you can see this rotates the whole plane in 2 seconds, and we want the tilt factor to tilt and then again normalize it after the rotation. So we want this to complete in 1 second, so duration 1, and we want this to normalize again in duration 1. Also we want this animation to play just right after this animation has completed, so we can pass the position parameter 1 here, so it will start in 1 second. So 0 second it will tilt and then rotate, and with rotation it will also normalize it back. So if we refresh it right now, you can see this card is tilting like that. It's rotating too much, so we can make it math.py divided by 2 and it will tilt. Okay, this looks good. Issue is related to the easing, so we can pass the ease defaults, just make it duration 2. It will not confuse us. Both of this animation will start at the same time, and then after the completion of this it will normalize it again back to 0. So it looks good, but now the easing is not good. So we can pass easing none to everything. Is none and is none, is none. So you can see it's much more uh, natural than that. It looks much more natural than that. Now let's try changing the background. So go to CSS and change the background color right here. So I'm using this color, this card of bluish color, tint color. This looks good. That's all for this video. See you in the next one. Peace.